Not numerical credit, but you got credit with me. Okay. Uh, this is the vectors coming to you live, physics in the AM. We're just going to have a quick, like, 20-second review. Yesterday, this was recorded before we had a name. Speed and velocity, we worked through this. And the idea of average speed is total distance over total time. We did an example. Now, velocity time graphs are more abstract than position time graphs. This is fairly simple. You're going 100 kilometers for 3 hours. Okay. The idea that the area under a velocity time graph gives you displacement, the distance and the direction that you moved from your original spot. Okay? Rectangle, it's fairly easy. But when you have a curve, but we're not going to use curves right off. When you have a curve, you'd use calculus. But with straight lines, you just break it up into geometric pieces you understand, triangles and rectangles. And you do the area of each one. I mapped it out. We did this together. Color-coded. Beautiful. Just beautiful. Okay. Now, here's where we left off. This is another vector problem because we actually took vectors as a separate section, 3. Why? I didn't have questions on it because we're going to use these vectors now to solve velocity problems, eventually with force problems. So we've got this. Let's think about this. A plane flies for 20 minutes going 120 kilometers east. We have the distance. And we actually have the displacement. Then the direction changes north 50 degrees east. It's really comfy. And the plane travels 70 kilometers in 13 minutes. What's the average velocity of the plane? Now, it's important I didn't say speed. It would be different. Wouldn't have a direction. All right? We know not to do average velocity by finding out the velocity in the first scenario and the second scenario and adding them together. Divide by 2. It's not that. Total distance. Total displacement in this case. Total time. Which means we got to understand our sines and cosines, etc. So let's go. You need a sketch. For my sketch, I'm going to use north as up. I'm only going to put the positive directions on it. And it so happens we understand. We understand west to be the negative. So I don't usually write that down. I usually just put north down. 20 minutes going, 120 kilometers. I'm going to draw that east, that one. That is east. This is Rutledge. Okay. That was at a time period of 20 minutes. Then the direction changes to north 50 degrees. 7. I can undo stuff easier than you guys can. What I'm going to do is actually make it so that I can. You're drawing my psych if you did what I did. Okay. We understand that north 50 degrees east means, I hope, that this is straight north, and I'm going 50 degrees towards the east, so a little over 45. And we'll go this. I'm not getting out of protractor. This is a rough sketch, right? Now, this is 50 degrees. I tend to like my triangles, right triangles, to be drawn like this, though, to the x-axis, I imagine, but in this case, when I do that, 50 degrees as 40 degrees left inside that corner. 90 minus 50. intuitively see that this side of the triangle is this going to the right, this side is going up. One's going east, one's going north. And it end up in the same spot as if you went just like this. That's what we're really doing in breaking down this triangle. Average velocity on the plane. Okay. So in a sense, we're trying to figure out. Started here, ended up here. You're trying to find out. Really, you're gonna gotta find all of the east and all of like that. That's disappearing because it just gets too messy. Everything. That's what we're figuring. So we're gonna break this down. I'm gonna put it in a T-chart kind of thing. We have the east-west column and the north-south column. Actually, everything is east and everything is north. So there's gonna be no maintenance on this. But the only trick we have to do is on the green triangle portion, right? In relation to the 40 degrees, that's the adjacent side, so it's cosine. I'm going to involve cosine. And that was 70 kilometers. So that means this is 70 kilometers on cosine 40. Likewise, this is 70 kilometers. I'll write this down and then backtrack and answer your question. I'm skipping a step when I'm doing this. This is the hypotenuse, 70. So if I think of this as, I'm going to just, that's disappearing, but I'm going to just change color and then erase what I wrote. Here's what I'm expecting you guys to know. Cosine of this 40 degrees here is adjacent over hypotenuse, right? Which is, we know that hypotenuse is 7. So if I solve for adjacent, it's just multiplying by 7. So that's where I get this expression. Likewise for the sine function. Does that make sense? I know you're sure is not always the same. Always. Okay. So that's the shortcut I'm doing because it's the same problem again and again. You just multiply it up that number times. There we go. Okay. Now, I'm going to make my T-chart of the east-west pole and the north-south. The first vector is easy. It's only east, so it's 120 kilometers. I can put a plus sign here. And because I put the plus sign, that's to the right. Keep track of the SIGN signs and 0. The other one, the degree machine. You use your calculator with the degree mode for sure. Not. You guys haven't started in radian mode in your pre-calc 30? That's when we're going to have mistakes, is because one class you need it in radian mode, one you need degree. I'll try to remember to ask you guys. I can't do cosine in my head, not 45 or 30. Let's go to 53.6. No, that's perfect. I had 3 digits, 70.0, so that's really 52 points. You could argue the angle though is only 2 digits. I'm not going to get hung up on safety. I need you guys to be aware of them. 70 kilometers times sine 44.995. What? He's 40. That's appreciated. Well, that's the north-south. The 70 times sine of 40? 44.995. So if you round it to a tenth position, the nines were going down. Right? The rest is just written. They're both positives. I didn't put the positive sign into it. The positive meaning east, positive meaning north. Let's add them. Okay. 120 plus 53. 173. Dollars. This one I am going to put it in the north just because, or east. That's possible. Squeeze them in stuff. Then this one here, I don't have 0.5 points. Kilometers. That's positive, so it's civil. This makes sense. I'm going to draw something on that diagram, but then I'm going to move it because it gets too messy. Let's see what I'm doing. I'm going to draw a rough sketch of what I just did. This is the blue triangle that we just figured out, but I'm going to just move it. Like I say. But do you guys see what I'm talking about there? If you add up all the east and all the north movement of those two segments of the journey, this is what we got. We get that you went 45. We get that you went 170.6. You guys kind of see what we put together with that T chart? I call it a T chart. I call it chart. Okay. That's what we just figured out. We want to get the average velocity of the plane. I actually didn't ask for this directly. Why? Because average velocity is total velocity displaced divided by time elapsed, right? This is why we're doing this. So we still don't have, we need the actual hypotenuse of that journey, right? And we know how. We got the math from grade 8 and 9. What theorem? What? Yeah. P theorem. Pythagorean theorem, A squared plus B squared. So, okay. I'm going to just say it's the square root of 173.6. I'm going to leave out the kilometers right now. Plus 45.0 squared. This is what we're looking for, right? I'm going to call it R. The resultant, though, is typical. I'm just square rooting right off the bat. R squared. That's tough stuff to do. 170. 45 squared. Not used to it. Let me get my calculator out. 173.6. I want you guys to verify this with me. 45. I get 179.337, blah, blah, blah. Yeah. Okay, I'm gonna call it 3 digits though, 179. And that is in kilometers. Now, we still don't have a direction, and if it's velocity, we need a direction. Yeah, it's northeast, but we gotta figure out to always give north, it's more north, there's no south component. We say, you're going north, and then how much over to the east? Well, there's two ways of thinking of this. Do you guys see what I was just talking about? We want to find out is the same as this angle here in the triangle by, you know, if you know how triangles work, stuff like this, 180, you know. So I'm actually going to get the angle by saying, yes, corresponding, by saying opposite over adjacent. That's a 10. 173 over 45. 173.6. So, I was just explaining what we're doing. So the angle is from the tan minus 1 inverse of tan of 173.6, the opposite, over the adjacent 45. And I let my calculator do all this. You want to find the decimal for that, so 173.6 over 45 first, you're welcome to do that. That's how depth you are with it. 173. So, I get 75.5. Now I have enough information to actually do the calculation we were asked for. This is all just to get the displacement. This is one of those questions where you do so much work and you forget what you're even looking for. We're looking for average velocity. Back to average velocity.
All that work is just the displacement.
This is child's play here. The average velocity, displacement of 179 kilometers. I'm going to put in north 76 degrees or 70. I guess it would still stay at 75 to 75. I have 75.5 degrees east. Divided by the time of. The time, I'm pretty sure, was given in minutes. 20 plus 13 minutes is 33 minutes. That one, we've got to come up with in hours, right? Kilometers per hour makes sense. So, I'm going to say 33 minutes. And I know intuitively I want the fraction of the hour is 60 minutes per hour if you want. And it comes out to be hours. You can just do it intuitively if you want to put it in the decimal 55. Science really appreciates you. That was a real good. There we go. Fine. Science.
I like cold in that day.
It is on the cooler side. I don't mind that.
So hot. I don't know.
gonna just do some math. The actual degrees doesn't get divided, by the way. It stays in your answer. 179 divided by 0.55. And I get 325, and I'm keeping it at 320. Units, kilometers per hour, and then the direction. All right,